Okay, so let's start. Today, inshallah, we are going to hopefully finish probability. Okay, as in not all of probability, but the category of probability that we started in the last class. All right, so I'll share my screen with you guys and let's get to work. Okay, so. Um, okay, so here we go. So in the last class, can you do question 7 from the homework? All right, sure I can. Just a minute. Okay, now I'm solving question number 7, and I want you guys to pay attention. Acha, by the way, there is, if let's say you're stuck at part 3, so hold on to part 3. What we're gonna do today we're gonna do a concept where we look into, just a minute, where we look into what happens if, okay, sorry. Yeah. So I'll look into this, Ibrahim. I'll look into the error that you're facing and we'll fix it, okay? All right, now I'm going to solve this question and I want you guys to pay attention. So basically, question number 7. Let's read question number 7. Let's see what it says. So it says one plastic robot is given away free inside each packet of a certain brand of biscuits, okay? There are 4 colors of plastic robot: red, yellow, blue, and green. Okay, this is a question from the homework. And then it says, and each color is equally likely to occur. All right, what does that mean, that each color is equally likely to occur? If there are 4 colors and each color is equally likely to occur, what does that mean? Unbiased, I agree. Unbiased or fair, but what will be the probability? 1 upon 4. So the probability of each color is going to be 1 upon 4. Okay, probability of yellow will be 1 upon 4, red 1 upon 4, green, blue, whatever, 1 upon 4. Okay. Nick buys some packets of these biscuits. Find the probability that he gets a green robot on opening his first packet. So the answer to the first part, the probability of green, in fact, the probability of any color is going to be 1 upon 4. Okay? Now, as far as the first part is concerned, that's it. Part 2 says Nick, he gets his first green robot on opening his 5th packet. All right. Now, if he's getting his first green robot on opening his 5th packet, what should happen in the first 4? What should he get in the first 4? He could get red, he could get yellow, or he could get blue. So in short, he should get green in the 5th packet, or the 5th turn is when he should get green. So what does that mean? This is what it means. 1, 2, 3, 4, 5. In the 5th turn, he should get green. Okay, so what should he get in the first 4 turns? He should not get green. Okay, so instead of trying to worry about whether it's red, blue, yellow, what we're going to do is we're just going to call them not green. Okay, and that's how we're going to work out the probability as well. So not green, not green, not green, not green. Okay, now if the probability of getting a green is 1 upon 4, then what will be the probability of not getting green? 3 upon 4. That's correct. Okay, remember the probability of an event happening is equal to 1 minus the probability of the same event not happening. Okay, so 1 minus 1 upon 4 gives us 3 upon 4. So G prime basically represents not green. Okay, it's up to you how you want to write it. So that means in the first attempt, he should not get a green color. In the second attempt also, he should not get a green color. In the third attempt also, he should not get a green color. In the fourth attempt also, he should not get a green color. Okay, so that means in the 5th attempt, he should get a green color, which is 1 upon 4. Now multiply this and get your answer. 3 power 4 is 81. And 4 to the power, okay, this side better work out. 4 to the power of 5 is 1024. So 81 upon 1024. And there you go. That's your answer. Now, don't worry about part 3. Part 3 has a concept which I want to explain to you guys today. And then you guys will be able to solve questions like part 3 and some other questions in this worksheet, which some of you can solve. I mean, those of you have done it, but those of you who haven't done it, that's for you guys. Okay? So I hope that helps. After today's class, by the way, after today's class, inshallah, you guys will be able to solve this entire worksheet. Not this entire worksheet, in fact, other worksheet as well. Okay? Hold on. Intishar, hold on. Let me teach you guys an important concept after that, because there are some parts in questions where you basically need to learn how many arrangements there are and multiply the probability by that. So just hold on. After today's class, inshallah, you guys will be able to solve all the questions from this worksheet. Okay? Now, what we're going to do today is, today we're going to see what to do when we have probability with multiple arrangements. All right? So that's what this concept is called, probability with multiple arrangements. And this can happen anywhere. Okay, this can happen in any probability question. Like for example, if the question says that one is red and the other is blue. Okay, now these kind of questions are not complicated. Why? Because we don't have a lot of arrangements to consider. It's just red blue or blue red. That's it. Okay, but what if, let's say we have multiple arrangements to consider? What do we do in that case? That's what we're going to see. So for example, let's learn this with the help of an example question. Here's what it says. A coin is tossed 5 times. Okay, so a coin, let me add unbiased. All right, so always look for these keywords, whether it's biased or unbiased. If it's unbiased, that means the probabilities of all the outcomes are going to be equal. An unbiased coin is tossed 5 times, and your task is to find the probability. Find the probability that, now here comes the first part. Head is obtained 5 times. Head is obtained 5 times. So anyone who can tell me what the answer to this part is going to be? Head is obtained 5 times. It's a pretty easy question. 1, 2, 3, 4, 5. Head, 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 head. Okay? So the probability of getting a head in the first attempt is 1 upon 2. What about the probability of getting head in the second toss? That's also 1 upon 2. Okay? And then just like that, 1 upon 2, 1 upon 2, 1 upon 2, 1 upon 2. So in other words, 1 upon 2 to the power of 5, which is equal to 1 upon 32. Okay? Now, this is one way to get head 5 times. Is there any other way that we can get head 5 times? No. Because even if I rearrange these letters, we still get the same thing. Okay? Now, let's do a following part where it says that head is obtained. Head is obtained the first 3 times. Okay. Now, let's write down how we can fulfill or how we can meet this condition. If head is to be obtained the first 3 times, what should we get? What should we get in the remaining 2 tosses? If head is to be obtained the first 3 times, what should happen in the remaining tosses? Head, head, head. What about the third and the fourth? What about the fourth and the fifth toss? Does not matter. Why does it not matter? It does not matter. Yes, the probability will be the same, but if the question says head is obtained the first 3 times, okay, what does that mean? That means the next 2 times, or in the fourth and the fifth toss, yeah, we should get tails. Okay, we should not get head. That means we should get tails. Now, yes, you're right. The probability does not matter. We get the exact same answer. Agreed. Okay. So it's going to be 1 upon 2 to the power of 5, which is equal to 1 upon 32. Now, is there any other way of satisfying this condition that head is obtained the first 3 times? No, there is not. Why? Because the order is specified. The question says head is obtained first 3 times. That means the first, second, and the third toss should give you a head. The fourth and the fifth toss should not give you a head. That means it's going to be tails. Okay? Now, focus on this part. Part 3 says that head is obtained a total of 3 times. Now tell me, what's the difference between the first and the second part? Oh, sorry, second and the third part. What's the difference between the second and the third part? No order. That's true. So part two was very specific that you should get head the first three times. Doesn't matter what you get the next two. That means, you should not get heads the next two times, which means you should get tails. Here the question says head is obtained a total of three times. So here's what we're going to do. Let's write down one way that we can fulfill this condition. Okay? One way that we can fulfill this condition. What could that be? That could be head, 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 tails, tails. Correct? Now, is there any other way that we can fulfill this condition where head is obtained three times? Think about it. Is there any other way? Yeah, that's true. Tail, head, 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 tail. Okay? Yeah, tail, tail, head, head, head. So the point is, we don't know how many there are going to be unless we figure out a way to count the possible outcomes. Okay? To count the total possible outcomes where we have three heads and two tails. Okay? So that's what we're going to do. That's what we're going to do. We're going to learn how you can find out a certain number of letters can be arranged when you have some repetitions. Okay? So what we will do, yeah, we'll do factorial. We will basically do a portion of permutations and combination. Okay, we're not going to do all of permutation and combination. This in detail you will encounter in when we're formally doing permutations and combinations. Right now, this particular concept is necessary for us to be able to do these kind of questions. That's why we're just going to do the factorial concept. Okay, so it's a very easy concept. We're going to do it with the help of an example, and then questions like these where you have to sort of sit down and think, how many ways you can fulfill that condition will become very easy. Okay, and we'll do some example questions as well so that you understand how the whole thing works. So let's say that you want to find out the number of arrangements. We call this the number of arrangements. So basically, what are we doing over here? We're arranging 5 letters, okay? And not all 5 of them are unique. Okay, so we need to find out how we can arrange these 5 letters when we have certain repetitions. So this is called number of arrangements of n unique letters. Let's see what happens if we have unique letters, okay? The way that we do it is n factorial. Okay, now I'm pretty sure everyone at this point should be familiar with factorial. This is something that you guys must have done in binomial. I hope everyone knows what factorial is. Anyone here who doesn't know what factorial is, please let me know now. Okay, so quickly tell me, how will we work out 5 factorial? Or what's the working of 5 factorial? Yeah, 5 into 4 into 3 into 2 into 1. Okay, 6 factorial, 6 into 5 into 4 into 3 into 2 into 1. Okay, so if you want to arrange n objects, sorry, it's not on n, it's off. Number of arrangements of n unique objects or n unique letters can be done by n factorial. Okay, so let's take the word Ali, for example. If I want to find out how many different ways the letters of the word Ali can be arranged, the way to do that would be simply 3 factorial. Okay, which is equal to what? Which is equal to 3 into 2 into 1, which is equal to 6. Okay, and let's write down all those 3, or all the 6 arrangements. So one is ALI. Okay, the other could be AIL, and then the third could be ILA. What else? Then we can have IAL. Yeah, LIA. That's also true. How many do we have? 1, 2, 3, 4, 5. And then LAI. Yeah. LAI. Now, how many do we have? We have 6. Can you think of a 7th possible arrangement using the same 3 letters? Is that possible? Think about it. No, it's not possible. Okay, so one way to do it is to manually write down all the arrangements. The other way to do it, the shorter way, is to use the factorial method. Okay, now we won't every time have unique letters. Okay, sometimes we'll have repetitions as well. Like for example here, we have head, 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 tail, tail. What do we do then? Let's write that down. Number of arrangements, the number of arrangements of n letters with repetitions. So how do we do that? Here's the formula. N factorial divide by P1 factorial into P2 factorial, so on and so forth, where P basically represents the repetition. So let's do an example. Let's take the word pop, okay, P-O-P. If I want to find out how many ways I can arrange these three letters, how do I do that? 3 factorial. How many letters do we have that are repeating? We have 2 P's. That means divided by 2 factorial. Okay, if you work this out, what do you get? You get 3. And let's write down those 3 arrangements. One is the way we see it, P-O-P. The other could be P-P-O. And then the third could be O-P-P. Can you think of a fourth possibility? Can you think? Nope, because it isn't there. Okay. Now, let me take a name. Let's take your name, Taha. Yeah, let's take Taha's name. Let's see how many arrangements we can have for this letter. 4 factorial. Why? Because we have a total of 4 letters divided by 2 factorial. Okay, what is that equal to? That's equal to 12. That means you can take the letters from this word, Taha, and have 12 different arrangements. Okay, let's take another name. Let's take another letter, in fact. Let's take the word. Let me think. Let me think of a word which has plenty of repetitions. Let's take the word committee. Okay. Does anyone know the spelling of committee? I know it has multiple repetitions, but I don't know the exact spelling. C-O, okay. C-O-M-M-I-T-T-E. Okay. C-O-M-M-I-T-T-E. Now, if I want to find out how many ways I can arrange the letters of the word committee, how do we do that? So we count all the letters. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 factorial divided by, now M occurs twice, so 2 factorial, multiplied by T, which also occurs twice, 2 factorial, divide by the number of times E is being repeated, which is twice, and the factorial of it. Okay, so let's work this out. 9 factorial. I hope you guys know where to find factorial in your calculator. Divide by 2 factorial into 2 factorial into 2 factorial. So what do we get? We get 45,360. Okay, so that means you can take the word committee, you can take the letters in the word committee and arrange it how many times? 45,360 times. Okay? Now, how does that help? How does that help us in solving this question? Any questions, by the way, regarding this concept? We will do this in detail when we're doing permutations and combination. For now, we just need the arrangement part of it. That's why this is all we're going to do. Okay, so I'm guessing no questions. Great. So now if I want to solve this, that head is obtained a total of 3 times. How do we do this? First, we write down one possible way that we can meet this condition. That is head, 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 tail, tail. And let's work out the probability of it. What would be the probability of getting head, 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 and tail, tail? It's going to be 1 upon 2 into 1 upon 2 into 1 upon 2 into 1 upon 2 into 1 upon 2. Okay? And then what do? Then we multiply it by the number of ways this can be arranged. By the number of ways the letters from this can be arranged. And that's going to be multiplied by 5 factorial, divide by 3 factorial into 2 factorial. So what this does is, now instead of considering them separately and finding their probability and then adding them up, what we've done is we've just found the probability of 1, and now we're going to multiply it by the number of ways this can be arranged. Okay, so let's work this out. I can see some of you have already given me the answer. So 1 upon 2, first of all, raised to the power of 5 into 5 factorial, divided by 3 factorial, and then divide by 2 factorial, which is equal to 5 upon 16. Okay, there you go. That's your answer. Now, we'll do some past paper questions as well, and I'll make a note of it, that what you have to do in scenarios like these. But for now, if you have any questions, feel free to ask. Okay, so when a probability condition can be fulfilled multiple ways, we find the probability of one way and multiply by the number of possible ways to fulfill that condition. Okay? So if a probability condition can be met or fulfilled multiple ways, then you just find out the probability of one and then multiply it by the number of ways you can fulfill that condition. Okay? So let's do an example so that you guys understand exactly what I'm talking about. Okay? So the example that I'm going to do is, let's do question number 2 from the worksheet. I know I gave it to you guys as homework, but there is a part of this question which you guys you could have solved previously also, but now you can solve it without any difficulty. Here it is. A triangular spinner has one red side, one blue side, and one green side. The red side is weighted so that the spinner is 4 times more likely to land on the red side than on the blue side. The green side is weighted so that the spinner is 3 times more likely to land on the green side than on the blue side. Okay, so all this sounds complicated, but it will make a lot more sense when you write this down. So we're doing the first part. How many colors do we have? We have red, blue, and green. Okay. Now, is it fair to say that the probabilities are equal? Can I say that? Can I say it's 1 upon 3, 1 upon 3? Of course not. Okay. Why? Because we can see that the red side is weighted so that the spinner is 4 times more likely to land on the blue side. The green side is weighted so that the spinner is 3 times more likely to land on the green side than on the blue side. Okay. So let's start with the blue side. Okay. The red side is weighted so that the spinner is 4 times more likely to land on the red side than on the blue side. So that means if blue is x, red is 4x. Okay. And then the green side is weighted so that the spinner is 3 times more likely to land on the green side than on the blue side. That means green is 3 times of blue. Okay. Which means it's 3x. Now what would be the sum of the probability? It's going to be 4x plus 3x, which is equal to 1. So x, which is representing the probability of blue, turns out to be equal to what? Turns out to be equal to 1 upon 8. Okay. Now you could have done this with x. You could have done this with maybe assigning any number. Okay. Either way, you get the same answer. Now, any questions as far as the first part is concerned? If yes, feel free to ask. Now let's do part 2.
Why did you equate it to 1?
Because what's the sum of all probability?
1.
1. That's why. So this 4x is actually representing the probability of red. X is representing the probability of blue. Green. 3x is representing the probability of green. That's why I equated it to 1.
So to find red and green, we just multiply it by 1 over 8?
Yeah. So if you want to find out, in fact, let's do that. If you want to find out the probability of red, that's going to be 4 into 1 upon 8. So that's 1 upon 2. Blue, we've already worked out 1 upon 8. Red is going to be 3 upon 8. Okay? We will need this in the next part. So let's just do it now anyway. All right. Now let's do part 2. The spinner is spun 3 times. Find the probability that it lands on different colored side each time. Okay? Now, just answer my question in yes or no. Is there only one way to fulfill the condition that we have in part 2? That the spinner lands on a different color each time? No, there isn't one way. In fact, there are multiple ways. Okay? So let's just write down one way. Can you just give me one way that we can fulfill the condition? Just give me any one way that we can fulfill the condition that we have in part 2. Red and blue. Okay, by the way, there are 3 colors. Okay, not 2. There are 3 colors. So let's take red, green, blue. Okay, anyone. Red, blue, green, blue, whichever, whatever you want. Doesn't matter. Okay, so let's take this. Now, let's find out the probability of red, green, blue. What's the probability of getting a red in the first spin? That's 1 upon 2. Then what's the probability of getting a green? That's going to be 3 upon 8. And then what's the probability of getting a blue? That's 1 upon 8. Okay, now instead of manually rearranging RGB and finding out how many different arrangements there are, all we can do is multiply this by 3 factorial. Yeah, that's it. We don't have to divide it by we don't have to divide it by anything because there are no repetitions. All right. So now let's work this out. 1 into 3 into 1 in the numerator, 2 into 8 into 8 in the denominator, and then multiplied by 3 factorial. Let's see what do we get. We get 9 upon 64. And there you go. That's your answer. Now, take a good look at it. Let me know if you have any questions. Let's do one more question. Why did you multiply it by 3 factorial? Here's how I did it. Tell me, is RGB the only way to fulfill the condition? No. Okay. Give me any other way. Give me any other way that we can fulfill the condition. RBG. What else? BGR. That's correct. Or 3 more to go. Could be R. No, wait, that's already considered. Could be green, red, blue. Yeah, green, red, blue. And I'm running out of space. Could be red, green, blue. No, we've considered that. Could be blue, red, green. Blue, red, green. Okay, 1, 2, 3, 4, 5. One more to go. Green, blue, red. Have I not considered that already? Okay, yes, thank you. Or green, blue, red. Okay, now tell me. One way is that we find out the probability of one and the other and then add them up. Okay. Or we find out the probability of just one and we multiply it by the number of ways we can arrange the letters RGB. So which one do you think is easier? Is multiplying by 3 factorial and giving the answer of power 6? No, it's not the same thing. Power 6 is something else. Multiplying by 3 factorial is something else. Okay, power 6 means that you're multiplying the same value a total of with each other a total of 6 times. 3 factorial is something else. So, to answer your question, the probability of getting red, green, and blue in this order, as we can see, is going to be 1 upon 2 multiplied by 3 upon 8 multiplied by 1 upon 8. Okay, this is going to be 3 upon 128. So this also is going to be 3 upon 128. This also is going to be 3 upon 128. This also is going to be 3 upon 128. This also is going to be 3 upon 128. This also is going to be 3 upon 128. So here's what we can do. We can either find out the probabilities individually and then add them up, or we can find, since all the probabilities are going to be the same, we can find out the probability of just one way to satisfy this condition and then multiply it by the number of ways we can satisfy the condition. Okay, so 3 upon 128 is one way that we can satisfy this condition, and we can do this a total of 6 ways. We can satisfy this condition a total of 6 ways, so we can multiply it by 6. Yes, we're using or here, we're not using and. So does that answer your question, Intishar? I hope I'm pronouncing your name correctly. Okay, great. All right, let's do one more question and then we'll move on to the next concept. Just a minute. Here, let's do this question. Jake attempts the crossword puzzle in his daily newspaper every day. The probability that he will complete the puzzle on any given day is 0.75 independently of all other days. So if the probability of completing is 0.75, what will be the probability of not completing? 0.25. Okay, so the probability of completing it is 0.75. The probability of not completing it, or C prime you can say, is going to be 0.25. Okay. Find the probability that he will complete the puzzle at least 3 times over a period of 5 days. Now, what's the key word? At least 3 times over a period of 5 days. So what does at least 3 times mean? First, let's discuss this. At least 3 times means what? Minimum 3 times. Okay. Yes or no? Order Order does not matter, I agree. It can be 3 times or more, not less. At least 3 times means it can be 3 times or more. So this means greater than or equal to 3. That means could be 3 times, could be 4 times, could be 5 times. Okay, can't be more than 5 because we're talking about a period of 5 days. All right, so remember, at least means greater than or equal to. At most means lesser than or equal to. Okay, at least means greater than or equal to. At most means lesser than or equal to. Okay, so in how many ways can he complete the puzzle at least 3 times from a total of 5? It's possible that he does it 3 times. Okay. Now, in order to complete the puzzle 3 times, it's not necessary that he completes it 3 times in the first 3 days and doesn't complete it in the next 2 days. Okay, that's not necessary, but it's possible, right? So complete, 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 not complete, not complete. Okay. Now, can we have more arrangements of these? Can we have more arrangements of these where he's completing the puzzle 3 times from a total of 5? Yes, it's possible. It could be complete, not complete, not complete, complete, complete. Okay. So instead of manually listing down all the possible arrangements, here's what we can do. First, let's find out the probability of this. It's going to be 0.75 into 0.75 into 0.75, or in other words, 0.75 to the power of 3. Okay. Multiplied by 0.25 to the power of 2. Why? Because the probability of completing is 0.75, and then 0.75, and then 0.75, and then 0.25, and then 0.25. Okay? Now what are we going to do? We're going to multiply this in order to consider all the possible arrangements in which he completes the puzzle 3 times from a total of 5. What do I need to do? Question for you guys. How do I find out the number of ways in which this can be arranged?
5 factorial.
5 factorial, is that it? Just 5 factorial? Don't I need to divide this by something?
3 factorial multiplied by 2 factorial.
That's correct. 3 factorial multiplied by 2 factorial. Okay, now let's work this out. Let's see what do we get. 0.75, close the bracket, to the power of 3, 0.25, close the bracket, to the power of 2, multiplied by 5 factorial, divided by 3 factorial into 2 factorial. So we get 135 over 512. Okay? Now, notice the question says at least 3 times. So you think this is it, or is there more? There's more. Now we have to consider the possibility that he completes the puzzle 4 times. And not just that, we also have to consider the possibility that he completes the puzzle 5 times. Okay, so let's talk about 4 times. What's one way to complete the puzzle 4 times? Complete, 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 not complete. What's the probability of this way? 0.75 to the power of 4, 0.25 to the power of 1. Now, how many arrangements can there be? Into 5 factorial divided by 4 factorial. Okay, so let's work this out. 0.75 to the power of 4 multiplied by 0.25 to the power of 1 into, yeah, this is just going to be 5 because 5 factorial divided by 4 factorial is just going to be 5. Into 5, so that's equal to 405 over 1024. Okay, so we've done 3 times and 4 times. As far as 5 times is concerned, it's going to be, there's only one way to meet this condition: complete, 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 complete. And the probability of this is going to be 0.75 to the power of 5. Do we have to consider any other arrangement where he's completing the puzzle 5 times from a total of 5? No. Okay, because there is no way you can arrange the letters here and make something else. Even if you, let's say, swap the 2 C's, or even if you swap 1 C with any other C, you get the same thing. So 0.75 to the power of 5 is equal to, let's work this out, 0.75 to the power of 5, 243 over 1024. Now, to get the final answer, it's 135 over 512 plus 405 over 1024 plus 243 over 1024. Let's see what we get. Make sure that you keep these values in fraction form only. Okay, once you get to the final answer, then yes, you can write it in 3 significant figures. But for as long as you don't, make sure that you keep them in fraction form. So here we have 459 over 512. Now, let me tell you something. If you're getting something, if you're getting a value which is already in fraction, it's best that you keep it in fraction. Okay, don't write it in decimal. Otherwise, you'll mess up when it comes to rounding off. Okay, now, any questions? If yes, feel free to ask. Okay, great. Now let's now let's look into independent and not independent, basically dependent events. All right, why? Because if you open up, if you look at the past papers worksheets that I've shared with you guys, you'll notice that you have a lot of these questions. By using appropriate probabilities, determine whether events X and Y are independent. Similarly, there's a recent question as well where, yeah, hence determine whether or not events A and B are independent. Okay, so we're going to learn how to solve questions like these. They're very easy, once again, given that you understand the concept. All right, so let's understand how this concept works. Now, you guys tell me before I formally tell you what independent events are. What do you think they are? What do you understand by the term independent events? They do not have anything in common. All right, that's one way to put it. What else? Yes, events that don't depend on any external factors. That's not entirely true, but yes, partially true. The probability, yes, exactly. So the probability of one event does not affect the probability of the other event. Okay, that's what independent events are. Independent events. Let's write down the definition. The two events are said to be independent. The two events are said to be independent if, sorry, not if, when the outcome of the first event does not affect the outcome of the second. Can anyone give me an example? Give me an example. Tossing a coin, that's correct. Because when you toss a coin, the probabilities are fixed. Okay? So, tell me if this makes sense. The probability of getting a heads in the second attempt is more if we get a tails in the first attempt. Does that make sense? If I say, or if somebody says, you're more likely to get tails second if you get heads first. No, it doesn't make sense. Okay? Because the probability of getting a heads or a tail in the first toss is the same as it is in the second, third, fourth, and it just continues. Okay? Just like that, if you're rolling a die, so the probability of getting any number is fixed, even if it's unbiased. Then also the probability is fixed. So it doesn't matter whether it's the first roll, second, third, fourth, the probability will be the same. Okay? So for example, it could be rolling a die and flipping a coin. So let's say one event is that you're rolling a die and the other event is flipping a coin. Independent? Yes, they are. Why? Because if let's say you get a 6 here, that does not impact or affect the outcome of flipping a coin. Okay, if somebody says that you're more likely to get a head if you get an even number on a die, that does not make sense. Okay, so this is an example of independent events. Just like that, any event with replacement. Okay, so if you're drawing and you're drawing with replacement, that also is said to be independent. What about without replacement? You think without replacement events are independent? Yes or no? No, they're not. Why? Because if you've taken out, let's say if you've taken out the color red, and let's say there are two colors, red and blue. Now, if you take out the color red in the first attempt, then yes, the probability of taking red in the second or blue in the second is different compared to if you take out blue in the first attempt. Okay? So, with replacement events, rolling a die and flipping a coin, or any event where, let's say, the probability of the first or the outcome of the first event does not affect the outcome of the second event, is said to be independent. Okay? Now, there's a formula to test it out. Okay, there's a formula which we apply in order to test whether two events are independent or not. Probability of A multiplied by probability of B is equal to probability of A intersection B. If this is true, if probability of A multiplied by probability of B is equal to the probability of A intersection B, that means they're independent. Acha, what does this mean? What have I written over here? Probability of A means probability of A, probability of B means probability of B. Probability of A intersection B means that both occurring together. If this is true, then the events are said to be independent. Okay. Now let's understand this with the help of an example. Normally the question will ask you to prove whether the following event is independent or not. Okay. That's how you will come across questions. So here's a question from the same worksheet which we're going to solve and see what's what. Now, even though it's a 2-mark question, but please don't shy away from sample spacing. Okay, if you do sample spacing, your chances of getting it right will increase exponentially. Okay. 2 ordinary fair dice, 1 red and other blue are thrown. Event A is the score on the red die is divisible by 3. Event B is the sum of the two scores is at least 9. Now remember, at least 9 means what? At least 9 means greater than or equal to 3. Now notice how I'm going to do the sample spacing over here. So horizontally, we're going to write the scores of one die. Vertically, we're going to write down the scores of the other. And here we have 1 red and 1 blue. Okay. So let's just divide this space here into red and blue. This means that the scores written horizontally are the scores of the red die. Okay. And the scores written vertically are the scores of the blue die. Okay. And what are we doing? We're adding them up. In one event, we're adding them up. So that means it would be a good idea if I record all the possible sums. Okay, so let's do that. We have 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. Okay. Now here's what we're going to do. Event A is the score on the red die is divisible by 3. Okay. So I'm going to underline where the score on the red die is divisible by 3. Okay. So where do you, can you point out where the score on the red die is divisible by 3? That is if we get 3 or if we get 6 on the red die. So that means this is representing that the score on the red die is divisible by 3. Here getting 5 means that the score on the red die is divisible by 3, 6, 7, 8, 9. And here also 7, 8, 9, 10, 11, 12. Why? Because these are all the numbers that we get when the score on the red die is 6, and these are all the numbers that we get when the score on the red die is 3. And why 3 and 6? Because 3 and 6 are numbers that are divisible by 3. Any questions so far? If yes, feel free to ask. If not, then let's underline event B also. Okay, I'll repeat. Event A is that the score on the red die is divisible by 3. Okay. Now let's look at all the scores one by one. Okay, and wherever this condition is fulfilled, I'll underline in red. Here we have 2. What's happened? How did we get this 2? We got this 2 because the score on the red die was 1 and the score on the blue die was 1. So is the score on red die divisible by 3? No, it's not. Let's move on. 3. How did we get this 3? We got this 3 because of 2 and 1. The score on the red die was 2, score on the blue die was 1. Is it divisible by 3? No, it's not. Here, the score on the red die is 3, score on the blue die is 1. That means the score on the red die is divisible by 3. Okay, so this is, in fact, this entire column in this entire column, the score on the red die is 3, which is divisible by 3. Okay, just like that, 4 is not divisible by 3, 5 is not divisible by 3, 6, however, is divisible by 3. So this also is when the score on the red die is divisible by 3. Why are we using sample spacing in event A when no sum is required? Okay, I agree. No sum is required, but we do need the sum, right? We do need the sum when the sum of the two scores is at least 9. Okay, sample spacing basically helps us see all the possible outcomes. And also, if you're thinking that we can find out the number of ways in which event A can be fulfilled, or you think you can find out the probability of A without making sample spacing, then that's also correct. Okay, you can do it without that as well. Okay, but doing sample spacing just helps us understand or helps us look at all the possible outcomes. All right? And just hold on, you will find the answer to your question also. Okay, if you're thinking right now, if you're thinking that we can find out the probability of A without doing sample spacing, you're right, but you'll find out why doing sample spacing is important. Okay, now event B is the sum of the two scores is at least 9. This is where I'm gonna underline using the color green. Okay, so where do we get 9? Here we get 9. Okay, and then here we get 9 and 10. Sum is great at least 9, and then 9, 10, 11, and then 9, 10, 11, 12. Okay, now part A. Part A says find the probability of A intersection B. A intersection B means what? A intersection B means A and B. That means the probability where A and B, they're both occurring at the same time. Now, if I'm looking for A and B occurring at the same time, what am I looking for over here? If I'm looking for A and B occurring at the same time, what am I looking for over here? 5 upon 36 is the correct answer, but my question is, what are we looking for? Am I looking for the ones that I've underlined in red? Am I looking for the ones that I've underlined in green? Or am I looking for something else? Yes, I'm looking for what I've underlined in red and green. Okay, because red is representing that the score on the red die is divisible by 3. Green is representing that the sum of the two scores is at least 9. Here it says A and B. That means I'm looking for the event where the score on the red die is divisible by 3 and the sum of the two scores is at least 9. Okay, so how many times has that happened? That has happened 1, 2, 3, 4, 5. So, which done? Does that answer your question? That why we're doing sample spacing? Yes, that's why we're doing sample spacing. Okay, now you may be thinking that why did we do so much working for just a 2-mark question? Well, we've done the working for part B as well. How? Let me show you. Hence determine whether or not the events A and B are independent. So how do we determine whether these events are independent or not? Here's how we do it. The probability of A intersection B, if they are independent, should be equal to the probability of A multiplied by the probability of B. Okay, let's see if they're independent or not. So A intersection B we've already worked out to be 5 upon 36. Okay, now let's find out the probability of A. Probability of A means the ones that I've underlined in red. Let's see how many of the scores we have that we have underlined in red. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 upon 36 multiplied by the probability of B. That means all the scores that I've underlined in green. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what do we have? We have 10 upon 36. If they're both equal, that means they're independent. If they're not equal, that means they're not independent. So 5 upon 36, there's not much we can do on the left-hand side. On the right-hand side, let's see what happens. 12 upon 36 multiplied by 10 upon 36, which is equal to 5 upon 54. Are they equal? No, they're not. So that means, are they independent? Not independent. That's what we say. Not independent. Now, take a good look at it. Let me know if you guys have any questions. We will do another question as well. A fair 6-sided die is thrown twice and the scores are noted. Okay. The total of event X is defined as the total of the two scores is 4. Event Y is defined as the first score is 2 or 5 are events X and Y independent? 4 marks. And just so you guys know, this is from May June 2019, paper 6, variant 1. So what are we talking about? We're talking about a fair 6-sided die, and in one event, we're looking for the total. Okay? So it's a good idea to do sample spacing straight away. So we have the first roll and we have the second roll. Okay, or you can say we have the, actually no, we just have one die. I thought we had 2 dice. So you can say that this is the first time we roll the die and this is the second time we roll the die. So the first time we roll it, we have these possible outcomes: 1, 2, 3, 4, 5, 6. Actually, let me switch to a neutral color. Okay, and then the second time we roll it, we have the same possible outcomes. Okay, now let's quickly write down their sums: 2, 3, 4, 5, 6. Sorry, 3, 4, 5, 6, 7. Sorry, 2, 3, 4, 5, 6, 7, and then 8, and then 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. Okay, now see if you guys can help me out over here. Let's look at the 2 events that we have. X, I will underline using the color red. Okay, Y, I will underline using the color green. So event X is that the total of the 2 scores is 4. Okay, the total of the 2 scores is 4. So how many times does that happen? 1, 2, 3. That's it. Okay. Event Y is, this I want you guys to figure out. The first score is 2 or 5. So the first score is 2 or 5. Can you tell me how many times does that happen? That the score on the first roll is 2 or 5. 12, that's correct. So the score on the first roll is 2, happens a total of 12 times. Okay, so here are 6 times the score on the first roll is 2, and since it's 2 or 5, so here are another 6 times where the score on the first roll is 5. Okay, since it says 2 or 5, we have to consider both. Okay, now it says are events X and Y independent? So see if you guys can solve this question further. I've done all the hard work. All you got to do is decide whether they are independent or not. And how do we decide that? I'll write down the formula. The formula is that the probability of A intersection B is equal to probability of A into the probability of B. If this is true, that means they're independent. If this is not true, that means they're not independent. I'll explain. So what's the probability that this total of the 2 scores is 4? That's 3 upon 36. Okay, they are independent. All right, that is the correct answer, by the way. What's the probability that the first score is 2 or 5? So here are all the possible ways the first score is 2, and here are all the possible ways the first score is 6. So 6 here and 6 here. So that's all together 12 over 36. Okay, so we have the probability here, it's xy instead of ab. Okay, so the probability of A is 3 upon 36 multiplied the probability of B, which is 12 upon 36. Does that answer your question, by the way? Now do you get it, where the 12 came from? Okay, great. Now let's see the probability of both these events occurring together. That means the scores that I've highlighted in red as well as green. So here we have 1, and yeah, that's it. That's it, 1 upon 36. So let's see if this is true. 1 upon 36 is equals to 36 upon 36 into 36. So this gets cancelled. 1 upon 36 is in fact equal to 1 upon 36. So that is the correct answer. Okay, and that's it. Job done. Okay, all good now? If you have any questions, feel free to ask. Next, what we're going to do is we're going to do conditional probability. No? Okay. That's fine. So, conditional probability is basically finding the probability under a specific condition. Okay, that's what it is. That's literally what it is. Conditional, and this is the last concept of probability. Okay, after this, you guys can Although now you guys can do this worksheet, okay? This worksheet has no conditional probability in it, but after this, I'll give you guys a conditional probability worksheet as well, which you guys can solve, okay? So, conditional probability. By definition, this is what it is. It means to find the number of favorable outcomes. It means to find the number of favorable outcomes under a specific condition. To give you an example, this is what a question can sound like. So let's say you're traveling by train or car, okay? And let's say you can either be late or on time. Now the question could be like this. Given that, okay, let's say the name of the person is Ali, okay? Given that Ali is late, find the probability that he traveled by train, okay? Or it could be like this. Given that Ali travels by car, find the probability that he is late. Okay, so whenever you see the word given, that is your cue that the question belongs to conditional probability. Okay, it belongs to the category of conditional probability. So what's the formula? The formula is the number of favorable outcomes within or with the given condition divided by, not divide by total outcomes, okay, because that's what normal probability is. But this is conditional probability. That means probability under a certain condition divided by the probability of the given condition. Like for example, let's say we're talking about Pakistan playing a cricket match, okay? So the probability of raining, not raining, and then losing and winning. So the question could be, given that it rains, find the probability that Pakistan wins the match. Okay, so now the denominator will have the probability of raining. Okay, the numerator will have the probability of Pakistan winning and raining. Okay, if it sounds confusing right now, don't worry. Once we do a couple of example questions, you will understand how it works. Just remember, this is what it looks like. Probability of A given B. Okay, how do we read this? This is how we read it. We read this as probability of A given B. Okay. Now what's the formula? This is what the formula is. The formula is the probability of A intersection B divided by the probability of B. Okay. That means A intersection B basically means A and B both occurring together. Okay. Upon probability of B means just the probability of B. Okay. Now a small note to help you identify what to put in the denominator. The probability of whatever is written after the word given comes in the denominator. Okay, so let's look at a question. And this is very easy. Let me tell you, this is very easy given that you understand the question. Okay, so this also is kind of a condition here. Let's look at a recent question, May, June 2020. Okay, here it is. This is, by the way, a conditional probability worksheet, which I'll share with you guys later. Okay, so it says here, Joanne goes to college each day by any of car, bus, or walking. Okay, the probability that he goes by car is 0.2, the probability that he goes by bus is 0.45, and the probability that he walks is 0.35. So first make sure, don't start making a tree diagram immediately. First make sure that you read the question carefully. When Joanne goes by car, the probability that he arrives early is 0.6. When he goes by bus, the probability that he arrives early is 0.1. When he walks, he always arrives early. Okay. So how many categories do we have? We have 3 categories and then 2 categories. 3 categories for the means of travel, 2 categories of whether he's late or early. Okay, late or not late, basically. Okay. Now, when we're making a tree diagram, first he has to choose between car, bus, or walking. Okay, so here's car, here bus, and here's walking. What's the probability that he goes by car? 0.2. What's the probability that he goes by bus? 0.45. What's the probability that he walks? 0.35. And then what happens? After he takes a car, there are 2 possible outcomes. What are the 2 possible outcomes? He can either be late or he can be early. So the probability that he arrives early when he goes by car is 0.6. The probability that he arrives early when Joanne goes by car is 0.6. So what would be the probability that he's late? Question for you guys. 0.4, obviously. Because you're either late or you're early. There's nothing in between, really. And then if he goes by bus, the probability that he arrives early is 0.1. That means the probability that he arrives late is 0.9. If he walks, he always arrives early. Okay, that's interesting. It should be the other way around. So if he walks, he always arrives early. That means the probability of arriving early is 1. So that means the probability of arriving late is going to be 0. Okay, so just so you guys know, whenever there's a 100% chance of an event occurring, the probability is 1 or 100%. So that's it. As far as the first part is concerned, this is it. Now, let's look at part B. Find the probability that Joanne goes to college by car given that he arrives early. Okay, so first let's break this down. And this is a 4-mark question. Look at the amount of space that you're given. More than enough. Okay, more than enough space. Find the probability that Joanne goes by car. Okay, and then you make a line here. And after that, you write the condition that's written after the word given. So what's written after the word given? That he arrives early. So what does that mean? That means we will find out the probability that he goes by car and arrives early divided by the probability that he arrives early. Okay, the probability that he goes by car and arrives early divided by the probability that he arrives early. Okay. Now, as far as the probability that he goes by car and arrives early is concerned, that is 0.2 into 0.6. Okay, so that's equal to 0.2 multiplied by 0.6. However, as far as the probability that he arrives early is concerned, how do we figure that out? If, let's say, the question said, find the probability that he arrives early. How many ways can he arrive early? We need to look into that. So you guys tell me. Don't tell me the probability. Don't tell me the final answer. Just tell me the number of ways he can arrive early. 3 ways. Okay, what are those 3 ways? Break it down. Break down those 3 ways for me. You're right, by the way. That's correct. The probability that he goes by car and he arrives early, the probability that he goes by bus and he arrives early, the probability that he walks and he arrives early. Okay? So we're not concerned. We're only concerned with whether he arrives. We're only concerned with the fact that he arrives early. We're not concerned with how he goes to work. Okay? So 0.2 into 0.6, or he walks, or he takes the bus, which is the probability of which is 0.45, and then he arrives early, which is 0.1, plus the possibility that he walks and he arrives early, which means 0.45 into 1. And that's it. That's your answer. Okay? I mean, this is not your answer. Obviously, you're not going to leave it like this. You are going to calculate this. So 0.2 into 0.6. Remember I said in the beginning that expect a lot of calculations and you got to have a good grip on your calculator. So this is why I said what I said. Divided by 0.2 into 0.6 plus, make sure that you type it as it is, inside the bracket. 0.45 into 0.1 plus, open the bracket, 0.45 into 0.1, close the bracket. So we're looking at 4 upon 7. Let me make sure I haven't made a calculation error. 0.2 into 0.6, 0.45 into 0.1, 0.45 into, 0.45 into 1. I accidentally wrote 0.1. Yeah, it's 8 upon 41. That's the correct answer. 8 upon 41, which is Acha, 0.35. Oh, yeah. 0.35. Sorry, my bad. Okay. I think I've entered it incorrectly as well. So 24 over 103. Yeah. You got 1 over 11? Okay, wait a minute. Let me just quickly double check. 0.45 into 0.1 into 0. Plus 0.35 into 1. Oops. Okay, let me check the answer. 0.457. Anyone is getting 0.457? No, wait a minute. Checking the wrong answer. This is 0.233. 0.233. That's the correct answer. Yeah. So 243 over 103, which is 0.233. 243 over 103 is the correct answer. Yeah. Yeah, this can happen. You can accidentally end up entering the wrong value in your calculator. That's very common. Just make sure that you keep your eyes and ears open, okay? And you just keep checking as you're entering them. Because what happens is, I'll tell you what happens. Normally, when you have like small calculations, the calculator works just fine. But when you have a lot of calculations, then the calculator slows down a little. So you got to make sure as you're entering all the values that the calculator is at speed or up to speed the same as you're entering them. Okay, so if let's say you're typing really fast, so maybe it won't slow down for the first couple of calculations, but then as the calculations get more and more complex and as they keep on getting lengthier, the calculator slows down. So maybe your speed of entering and the calculator's speed, they're not matching. So you got to make sure that you keep checking that whatever you've entered, whatever you wanted to enter, has actually been entered in the calculator. Okay. All right. So any questions as far as this example of conditional probability is concerned? If not, let's do another question. A slightly simpler one. I'll give you a simpler question to solve. So anyone who has the answer to the first part? Find the probability that the student plays the guitar. 41 over 90, that's correct. So all you got to do is find out the total or number of students who play the guitar. That's going to be 44 plus 38. Let's see what that is. 44 plus 38, that's 82. Okay, and then sometimes in a question like this, you're given in the question the total number of students, so that's 180. So 82 over 180 will give you the correct answer, which is 41 over 90. Okay, now do part B. So anyone who has the answer to part B? Probability that the student is male given that the student plays the drums. 11 upon 31 is the correct answer. Good job. So how will we do this? Find the probability that the student is a male given that the student plays the drums. So probability of male given drums. That means we'll find out the number of students, the male and who play the drums, divide by the number of students who play the drums. So what's the number of students who play the drums and what's the number of male students that play the drums? That's 11 divided by the number of students who play the drums. So what's the total for the number of students who play the drums? That's 31. So 11 upon 31 is the correct answer. Even if you take the probabilities, like for example, if let's say you take the probability of the number of male students who play the drums, so that's going to be 11 upon 180 divided by the probability that the student play the drums, that's going to be 31 upon 180. So 180 will eventually cancel out and ultimately you'll be left with 11 over 31 only. Okay, does that make sense? Achha, by the way, wait a minute. I just realized that this question had a following part also. Determine whether the event the student plays the guitar and the student is female are independent, justifying your answer. Okay, so how do you justify your answer? You use the formula and you show the working. And then that's how you conclude. So quickly solve this and then I'll give you guys one last question to solve and that'll be it. Not independent? All right. Let's see. So How exactly are we going to do this? Determine whether the student plays the guitar and the student is female or independent. So let's find out. First, let's determine the number of students that play the guitar. So, how many students play the guitar? 31. Okay, so 31 upon 180 multiplied by the number of female students. So, what's the number of female students? 42 plus 38 plus 20. So, the probability that the student is female is 100 upon 180. If this is equal to both the events occurring together, 82. No, that's not 82. 42 plus 38 plus 20. 82 students play the guitar. Oh, okay, yeah. I don't know where 31 came from. Sorry. 82. Yeah, 82 students play the guitar. Thank you. Acha. Then, if this is equal to the probability of a female student playing the guitar, then that means this is independent. So, what's the probability of female students playing the guitar? That's 38 upon 180. So, clearly, this is not equal. That means not independent. All right. Thank you. Now, one last question, and that will be it. Here. So here's the first part, and then part B and part C. I'll paste them here so you guys have everything in front of you. Don't take the tree diagram lightly, okay? If you get the tree diagram right, you will get the following parts right as well. I will give you 5 minutes. So you have till the end of the class. So the first part is asking us to draw a fully labeled tree diagram to represent this information. What information? Now let's read. On Mondays, Rani cooks her evening meal. She has a pizza, burger, or curry with probabilities 0.35, 0.44, or 0.21. Okay. So let's make a tree diagram with 3 branches, 1, 2, and 3. Here, let's write down pizza, burger, and what's the third? Curry. So the probability that she has that she cooks pizza is 0.35. 0.44, 0.21 respectively. Okay. Then after that, there are 2 possible outcomes. One possible outcome is that she has some fruit, and the other is that she does not have some fruit. So the probability that she has fruit with pizza is 0.8. Sorry, 0.3. 0.3. Okay, and the probability that she does not have fruit is 0.7. Okay. Then with burger, the probability that she has fruit is 0.8. Okay, that means the probability that she does not have fruit is 0.2. Then with curry, the probability that she has food is, let's see what it is. When she cooks curry, she never has any fruit. Okay, that's interesting. 0, that means no fruit is 1. Okay. Now let's see what the question is saying. So you get 2 marks for just making a tree diagram correctly. Find the probability that Rani has some fruit. So she just gotta have some. She just gotta have some fruit. Okay. Whether she has it after pizza or after burger or after curry. So that means we need to consider all possibilities. Okay. So we need to consider that she cooks pizza and has some fruit. That means 0.35 into 0.3. Let me make sure of that. Yeah. Then the probability that she makes a burger and has some fruit. So that means 0.44 into 0.8, or the probability that she makes curry, which is 0.21, and then she has some fruit, which is not likely at all. Okay. So anyone who can tell me the answer to this? In fact, you guys have given me the answer. It's 0.457. 0.457. Okay. Thank you. Now let's do part C. Part C says find the probability that Rani does not have a burger given that she does not have any fruit. Okay. Does not have a burger given that she does not have any fruit. Okay. Now here we have already worked out the probability that she has some fruit. Okay. So if we worked out the probability that she has some fruit, which is 0.457, how will I work out the probability that she does not have any fruit? Do I need to do all the hard work all over again? Well, I can. The same way we worked out the probability that she has fruit, we can work out the probability that she does not have some fruit. That means pizza, no fruit, burger, no fruit, curry, no fruit. Or if we take the easy way out, which we should, all we got to do is 1 minus the probability of having fruit. The probability of an event not occurring equals to 1 minus the probability of that event occurring. So that gives us 0.543. Okay, so the probability that she does not have any fruit is 0.543. Okay, now let's break this up. Find the probability that Rani does not have a burger. That means probability that she does not have a burger given that she does not have any fruit. So that means in the numerator, we will take the probability of no burger multiplied by the probability of no fruit, okay, divided by the probability of no fruit. Now we've worked out the probability that she has no fruit, okay? That's going to be what? That's going to be 0.543. Now what about the probability that she does not have a burger and does not have fruit? How will we work that out? The probability that she does not have a burger and does not have any fruit. How many ways is that possible? Think about it. How many ways is it possible that she does not have a burger and does not have fruit? If she's not eating a burger, then what is she eating? What could she be eating? Curry and pizza. That's correct. So that means now in the numerator, I need to consider the probability that she has curry and no fruit. Okay. And she has pizza and no fruit. So pizza, no fruit, that's 0.35 into 0.7. 0.35 into 0.7. And then the probability that she's eating curry, which is 0.2, multiplied by the probability that she's not eating any fruit, which is very likely if she's having curry. So if you work this out, you get 0.455 divided by 0.543, which is equal to 0.837. And there you go. That's your answer. That's how you earn these 4 marks. Not 4 actually. 4 plus 2, 6. 6 plus 2, 8. That's how you earn these 8 marks. Now, any questions? If yes, feel free to ask. If not, then this is it. This is all there is for today. So I'll stop here. I'll see you guys inshallah in the next class. Take care everyone. Allah Hafiz.